So good afternoon, and we started finally this class. Went to the wrong room where everything was working. So today I would like to make some comparison between air breathing and rocket propulsion in terms of basic performance parameters. We had first to complete yesterday discussion. We at the end of yesterday's class we see that we have, for let's say, if we are throwing stones, we have the result that thrust should be F equal to mue. Whereas if I'm considering a fluid, I have to consider also pressure that we have at the exit of the engine, and in this case we have so many particles characterized by a given pressure, which is different in general from the ambient, and so we have another expression that that is the following, of course, that everybody of us knows very well. So we have from these expressions, but we see that we have no dependency on flight velocities, and this is an important difference with respect to air breathing propulsion. So this is why I'm underlining this, and at the end of yesterday's class, I said that if we take the same control volume and we consider this control volume instead of being in a still environment, if I think of a wind tunnel, so we have some free stream velocity, the result doesn't change. So let's have a look. If I consider the same problem as yesterday, here with our rocket and let's say our balance, and we have the control volume. Can you see it? We have that here we have a given V0. V0 is also here and also here. This is a wrong control volume. Should be this one, of course, with the exit of the jet from the rocket. So we have an area here AE, and we have that if we consider this area here plus this one, this will be altogether, this A and B makes together A left minus AE. This is A left. So of course we have to consider, as I mentioned yesterday when we started with this balance, we have to consider both mass and momentum balance. The mass within the control volume is changing because we have an exhaust of mass through the engine, and so we have that our, let's say, derivative of the control volume mass in time will be decreasing by a rate dot me. If we look to what enters and leaves this control volume, we see that we have this change of mass will be also the difference of what is entering and exiting the volume. So we see that we have here some mass entering on the left. Then in principle we have some mass which is entering from the top. And with a minus because we know that mass is exiting from the right. So what is coming in from the left is just rho UA, so in this case rho V0 by A left. What is exiting from the right, there will be rho A B0 by this area I indicated with A and B. And so you see here it will be rho V0 A left minus AE. And of course we have also the mass exiting through this cross-sectional area. I apologize for this drawing, but yesterday I made a better one. So you have that as a reference. And so we have here rho E, UE, A, E. Okay. So if we look to this balance here, we have minus, and this is, of course, this is dot ME. So we see that we have minus dot ME is equal rho A with 0 A left plus dot M top minus rho A with 0 A left minus rho A with 0 AE. So we see from here and then, minus dot ME. There are these three terms making together our dot M right. So you see here that we can cancel these quantities and also this and this. And at the end we see that this I made probably this is plus because there is minus and this minus dot M right. So you see that we have that on the top we need that there is some mass exhausting the control volume from the top, and this will be because this entering mass, this is top and this is minus rho A with 0 AE. So we need that there is some mass flow rate exiting here. Of course, this will be a small amount if we consider a big volume, and the velocity will be more or less directed as V0. We have a small component that allows us to balance the masses. So if we pass now to the momentum balance, force momentum balance, we have, again, you can see here, of course, it will be pressure PA, except on this section where we have the pressure PE. So we can consider different forces acting on the control volume, and there will be, of course, PA by the left area. Then, of course, we are considering only the forces acting in the thrust direction, which is our x-axis of that drawing. So PA A left minus PA that multiplies, let's say A left minus AE, considering that part A and B that I mentioned before, where we have PA. Then we have to consider that on the corresponding area AE we have PE AE, and these are all the pressure forces acting on the left and on the right. Of course, on the left is a force oriented from left to right, and on the right we have a force directed in the opposite direction. So we have this minus. And of course we have to add from the reaction of the balance F, that is our measure of the thrust, which is directed again from left to the right. So it's F. These are the forces acting on our control volume, and to them it corresponds a change of momentum. We are considering a steady state operation, nothing is changing in time except that we have this jet. So we have to show here on the right the difference between the outgoing and incoming momentum. So what is the what is leaving our volume? And we have to consider the mass flow rate exiting from the top. We have, let's say, dot M top with 0. This is an exiting momentum in the x direction is exiting from the top, because we have a component V0 in the x direction, and we have a mass flow rate exiting in the normal direction, but with that moment component in the x direction. Then we have, of course, what exit from the right, and so we have to consider rho A V0 squared by the area, because it's, of course, mass flow rate by V0. So we have rho A V0 by V0, and in particular the area will be on the right with this one corresponding to the velocity V0, plus we have a term corresponding to the area AE, where we have, of course, different quantities, and in particular we have rho E V UE AE, which is dot ME by UE again. So at the end we have dot ME UE, right? On the left, so we have an incoming momentum that we have to subtract, and it will be rho A V0 squared A left. So recall that this is rho A V0 AE, and you see that if you consider this, we can simplify. So we have rho A AE V0 squared that exactly balance this term. So this term here cancel with this, and then we have rho A V0 squared A left here and here that also cancel out. Finally, if we look on the left hand side, we see that this term cancel with this other one. At the end, we have the same result as yesterday. We have that here, we have that PA minus PE by AE plus F is equal to dot ME UE, or again F MUE plus PE minus PA. Okay. This should is a proof of the fact that there is, even if you are in a wind tunnel with some velocity, we have no changes for this expression, which remains independent of the flight velocity, of the external velocity. So there is another issue that appears here, that is the following. We consider that we have a different expression from what I called, we are throwing stones or rocks, what do you prefer, and we have that .MUE, and here we have also this pressure term. What is the meaning of this pressure term? This pressure term means that if our fluid exits at a given pressure, it will continue to change its velocity until it reaches the ambient pressure. So if we have a pressure at the exit greater than the ambient pressure, actually there is a force that allows the flow to expand more, to accelerate more. So at the end, if we look to our fluid particle very far away from the engine, we'll find it with a different velocity compared to what it has at the exit of the rocket. And what we have considered, when we consider the energy that we have provided to this particle, we have to consider everything. So at the end, we realize that the final energy of this particle is exactly the one that, if we don't consider any dissipation, any friction, any, let's say, other phenomena, will be the kinetic energy of the particle at an infinite distance from the engine, from our rocket. So I can try to convince you about that, again with a control volume, to explain the meaning of this term. Because if we consider now control volume starting from the exit, so we have here our AE, and let's suppose that we have here given PE and here PA. What happens here is that this jet, probably inside our control volume, will continue to expand, and at the end we have here a pressure PA everywhere. So here, of course, we have UE. Here, let's come back to the case where we have U equal to 0. You see here to have less term to be balanced. And so we have that here, there will be some other velocity, let's say U infinity. So if we make our momentum balance, what we see here is that in this case on the left we have a difference. We have PA by area left minus area at the exit. This is PA. Then we have PE by AE. We have no other forces except pressure in this case on our control volume. So we have these forces on the left, and we have on the right everywhere is PA, so we have PA, A left. So A left is this area here. I maintained the nomenclature of the previous example. And this will be equal, these forces acting on this control volume will be equal to the difference of momentum that we have at the entrance and at the exit. That means only through this AE and on this part here that, let's say, AE infinity. But of course we have also the mass balance that tell us that the mass flow rate here, let's say dot ME and dot ME infinity is the same. So what we can see is that on the left, or better on the right, we have, so the exit momentum, the final momentum exiting at control volume will be dot ME infinity by UE infinity, whereas on the left we have our dot ME UE. So of course these are the same. And here I can always simplify something. And we have here that PA minus PE AE plus no, it's minus, sorry. Let me correct. We have PE minus PA AE. This is what is remaining on the left hand side of this equation. Then I bring this dot ME UE on this side, and this will be equal to dot ME infinity UE infinity. So you see that, then this, of course, I can cancel this because they are equal. So you see that we can identify a new velocity that replaces all this term. This is exactly F. So you see that we can express this force with exactly the same expression we have seen at the beginning, or with the case of zones, provided we consider this far field velocity. So this simplified the expression, is convenient, and has this kind of meaning. It's an ideal velocity that represents not only this impulsive term of the thrust, but also the pressure thrust. So we will refer to this term as the equivalent exhaust velocity or as the effective exhaust velocity. We can use here UEQ is a way I often use to identify this term. In the literature you can also find C for this effective exhaust velocity. So what's the difference with if we consider, so for us now at this point we can express our thrust of a rocket with this expression. And we can compare this with what happens to an air breathing engine. In this case we make this kind of control volume with our bleeding engine. Here we have the reaction force F, and here we have some stream tube through which we collect the free stream air, so that we have here a given velocity uniform, or with 0, and also a given PA. Of course, we have here a different pressure and velocity, and here we have the same as upstream. So we already know from what we have just seen that there could be some mass flow rate on the top, and in particular, we know here there will be also some fuel mass flow rate entering our engine from outside. And so we have that dot ME will be equal to dot MA plus dot MF, where this mass flow rate, A, is the one entering through this stream tube the engine. And of course, dot ME is mass flow rate exiting the engine, that will be given by the A mass flow rate plus this fuel mass flow rate. And we have that we can consider the remaining part of the left-hand side and the remaining part of the right-hand side and the top boundary also be characterized by different mass flow rate, and in particular what comes in through the left boundary, except what goes within the engine, must be equal to what exits on the top and on the right, except the area through which we have the exhaust from the engine. With these mass balances, we pass to the momentum balance, and there will be again our force, reaction force, and then we have the pressure forces. All the area with PA on the left, and on the right there will be again the pressure PA minus PA, my left, minus AE plus minus PA, PE. AE. So the pressure forces are exactly the same as before. We have to consider now for the momentum, we have that with this equation for the mass balance, all terms which are not in the inlet of the stream tube and on the exit of the engine cancel out, and so what remains is dot ME UE minus dot MA with 0. And you see here what you already know, that we have as the expression of the thrust a term clearly dependent on the flight velocity. Actually, we can identify a term which is similar to what happens to a propeller-driven engine, which is, let's say, if we write this dot MA UE minus V0 plus dot MF UE plus PE minus PA AE. This is like a propeller, and this is like the expression of thrust of a rocket. It's not surprising because we have that this additional mass flow rate is something that we have on board. Of course, we can identify also here free stream velocity, and here this is done considering grouping this PA minus the pressure term within with the exhaust velocity, and so usually we consider for an air breathing jet engine dot ME UEQ minus dot MA with 0, with the meaning that within this term there is also, this is dot ME UE, but you consider here also for the exit mass flow rate also the expansion up to infinity, let's say, far away from the engine. So if we like to consider a comparison of different kind of propulsion devices, we have rocket, we have air breathing engine, and we have, let's say, a propeller driven engine. So if we would like to consider what happens in terms of use of available power to get this thrust, you know that you have to consider different losses, and I give you some. Probably this is enough. These are arrows. Saying that if I have this available power, only this part will be useful. This useful power means the work done by thrust force. So if this is V0, this is V0 also here, but we have to consider different possible losses. One possible loss is connected to the residual kinetic energy of the jet. Other possible losses are related to residual thermal energy of the jet, if I consider a thermal rocket. And then we have also other losses. And this, so if this is the residual kinetic energy of the jet, this is overall the energy that we have given to the jet, and then we have other losses here. And this can be, let's say, up to 70% the useful power, but we have to consider that also this residual kinetic energy of the jet can be also as high as 50%, and the same is true for the unavailable thermal energy. So these are unavailable thermal energy, unavailable kinetic energy, because this is the residual power of the jet. So we can try to understand how efficiently we are using our available power by comparing with this quantity. One interesting thing here is to discuss briefly this jet power, because we provide our fluid with a given amount of energy, but we don't use all the energy that we have given to the fluid. So in terms of power, there is something wrong, there is something lost. The residual energy is just, as I said, the kinetic energy of the jet, so we can write this for the different cases this residual power for the rocket is just this quantity, because I have to imagine that I'm moving at a velocity v0 and I'm exhausting the jet at a velocity ue compared to with respect to the moving vehicle. So the velocity of the jet with respect to the vehicle is ue minus v0. And this is something that we see as a residual energy. We can imagine that we find if we see this rocket flowing in front of us, or this aircraft flowing in front of us, we see that we have in one direction or the other this jet that it was first before we had this engine. There was something still. Now there is something moving. Consider that if you are considering a propeller or an air-breathing engine, this is clear. We have some air that is still, and then it is moving. So we have left some energy to the atmosphere. For the rocket, something slightly different, because there is something there that was not there before. Okay, so this makes a difference, and we will comment this at the end. In general, we see that we have a jet that is moving, and so you see this can be something that is lost. So similar expressions. This is UE, UQ is the same. I use the same for all the terms. So if you would like to see how much of the energy we have conferred to the jet we are using, we should compare this propulsive efficiency, which is the useful power divided by the sum of useful power plus the residual power of the jet. And we can just elaborate these expressions and just sum. Of course, here you have this PU is thrust by V0, and of course we have these different terms. You have to just make sum. So let's consider for the rocket, I have this Pj will be dot mp u e v0 plus 1/2 dot mp u q minus v0 squared, and by little algebra we can obtain this is 1/2 dot mp u q squared plus v0 squared. And this ought to be something strange. I would expect that the power of the jet is just 1/2 dot mp by uq squared. This is kinetic energy of the jet, but you have to consider that before doing this, we have brought this propellant at the velocity v0 before giving it a further kinetic energy. So I already given this energy to the jet. So this is why I have this other term in this expression that comes, however, you see easily from the sum of something that is clear. The work done by per unit time by the thrust and the residual power of the jet. And you can see also, let's say, the third expression we write for the propeller case. This is the thrust and this is the kinetic energy. This is dot MA, and the result is this time is different. In this case, what we have is UE minus V0 squared. So I don't want to spend too much time on the repeating engine because it's slightly more complicated because we have .me and .ma, and so I would like to go straightforward towards the result. You can obtain, let's say, equal to, okay, you write everything, and then we have here 1/2 .ma. Not surprising, yeah. It's something that we can expect. We have the propeller side is minus, and let's say the rocket part .mf. So you see that we have this term. The first term is identical to what we have with the propeller, and the second term with .mf is the same as we have with the rocket. Usually in repeating engines we neglect the second term because the fuel mass flow rate is typically, let's say, less than 10% of the air mass flow rate. So we can pass now to the propulsive efficiency, making the ratio of Pu over Pj, and for the rocket we have our propulsive efficiency as .mp u q v0 over 1/2 .mp u eq squared plus v0 squared, simplify, and 2 times u eq v0 over u e squared plus v0 squared. If we divide everything by u eq squared and introduce the ratio v0 over u eq, we see that here it becomes twice nu and 1 plus nu squared. Similarly, if we neglect this term, we have the same expression for the two other cases, and we have 1/2 .ma u squared minus v0 squared, and here we have .ma u eq minus v0, simplify 2 times, and here we have v0, of course. And what happens here is that we simplify uq minus v0, and so it becomes 2 times v0 ueq plus v0, and we make again appear this ratio, and you have 2 times nu divided by 1 plus nu. Okay, note that for the second case, it must be nu less than 1. The velocity must be less than the exhaust velocity, else we have a negative thrust. Of course, it's a condition to get thrust is that the jet has to increase the original velocity of A, else we are not providing A. So it means that if we look to the behavior of this propulsive efficiency as a function of this ratio, we can consider the curve for the say for the air breathing or propeller engine, and another one for the rocket, with the difference that this is going to 0 at infinity. So this is 1 also. And the difference is that, of course, this curve mathematically continues, but we don't consider this branch because it's for nu greater than 1 that must be excluded. This is not the case for the rocket. So in both cases, what we see is that the maximum propulsive efficiency is when the residual energy is 0. That means that we have something which is not moving with respect to the atmosphere, that corresponds to 0 thrust for the air breathing engines. But this is not the case for the rocket, because there is no dependence on flight velocity. So if these tell us that for air breathing engines, the best solution in terms of efficiency corresponds to the case where the velocity of the jet is as close as possible to the flight velocity, this information for the rocket, as I mentioned before, is something different, doesn't help us too much. But usually we see this kind of plot, and also other considerations can be done, because this actually it works at the best if you are considering a constant velocity flight. Typically with a rocket we are not doing a constant velocity flight, and so this doesn't help too much. So with rockets in principle we can achieve this propulsive efficiency equal to 1, but this doesn't tell us everything. Probably something better can be understood in terms of overall efficiency, and which includes, let's say, which is the ratio between useful power and the available power. So there is in between also the efficiency of the engine in converting the available power to the jet power. So we have some source of power, we use this to accelerate our jet, we give some energy to the jet, and then we try to convert this energy to useful power. But if we are considering, as I mentioned, a constant velocity flight, this, as let's say, this useful power has a straightforward meaning. For a rocket is something different, despite we can always consider that in fact this is thrust by velocity, it represents a change of kinetic energy. It's just this force by the velocity, and this force is also m dv dt, and so we see that if we replace this will be f by v is this one, and so is m ddt v squared half, and if we consider m constant is exactly the change of kinetic energy. So
arriva di ritardo, però non si vedeva, ma arriva di ritardo.
Arriva di ritardo. So we have some kind of meaning of this quantity. So we have these efficiencies. Actually, I could say also that if you look in more detail, because here you have this M, here M is not constant. So actually, this useful power should consider also the fact that the change of kinetic energy, rather than consider just thrust by velocity, you should consider the change of kinetic energy, and we have a different expression for the propulsive efficiency in this case, slightly different. But it would be something like, let's say, degrees more. But let's make another step. Let's say that is exactly this that matters to us, having a good efficiency, good exploitation of power. Our goal is to have, I recall that, yes, what we say is that we have to reach a given change of velocity. This is our goal. We have to provide given change of velocity to some payload. This is our goal. And probably one important thing is to do this with the least amount of propellant. We would like probably to save masses as we are as we are flying. So if we have to generate thrust to get some change of velocity, probably we are interested to see some kind of specific consumption, as we do with our cars, as we do with our airplanes. And in airplanes, for instance, we consider thrust-specific fuel consumption that tell us how much fuel we need to generate a given amount of thrust. And so, for instance, this is represented as TSFC, thrust-specific fuel consumption, and this is the ratio between the fuel mass flow rate and the resulting thrust. So if you are considering a rocket, what's your consumption? It's what we have on board. So we should consider our propellant mass flow rate divided by the thrust. This is a general expression. It's always valid, independently of what, provided we are using some kind of propellant to generate the thrust, we have to consume some mass, and this, of course, is an instantaneous measure of what is happening in this sense. This quantity, if you are considered, again, constant velocity flight, can be related to this overall efficiency, ratio of U over PAV, that of course is made of an internal or thermal efficiency and our propulsive efficiency. Of course, this eta TH is the ratio between PJ and PAV. And so if we increase the propulsive efficiency, we increase the overall efficiency, and we can see that we also reduce the thrust-specific fuel consumption. I ask you, I stop a moment just to say that please, today I think that it's better we continue without a break because of the delay and the late time to finish by 6 o'clock. So we can here, if you are considering a bleeding engine, the available power can be, if you are considering some, of course, some conventional engine using some fuel. So as we have this data MF, so we have an available power that will be data MF by this heating power of this fuel. We can see that this TSFC is data FQF V0 and QF V0 F. So I just multiply numerator and denominator by QF V0. So this is the power released by unit fuel that tell us about our available power. And so doing this, we recognize it here the available power. We recognize F V0, which is the useful power, and so we see here that we have V0 over QF by P available divided by PU, or 1 over the overall efficiency. So the higher the efficiency, the less the trans-specific fuel consumption. When we are considering rockets, as I mentioned, we are not focusing on this constant flight velocity. So which velocity we should use here? An average velocity? What would be the meaning? What we can see, we can go directly to this expression and see that from thrust expression, we can directly identify a quantity which is significant to measure our consumption. So we see here that TSFC for a rocket, F is that the thrust is that MP by this equivalent velocity or effective exhaust velocity. So we see this expression, an important one that tells us the higher the exhaust speed, the less the trans-specific fuel consumption. So it seems that the higher the speed, independently of the flight velocity, independent of anything else, the less will be the needed propellant we spend to get a given amount of thrust. Our goal is to get a given amount of thrust for a given time, and of course it's interesting to see how much propellant we spend per unit time so that we can integrate and see what would be the overall amount of propellant we need. So this quantity plays a fundamental role in all in rocket science, as this is the inverse of this velocity, we see that this velocity is the important parameter, and instead of saying or looking to this trans-specific fuel consumption and saying that it should be as small as possible, we say it's the same to say that this velocity must be as high as possible. So we take this quantity as the main quantity for the study of rockets. It's the most important parameter. And this is exhaust velocity that measures the ratio between the thrust and the propellant mass flow rate we need to spend to get that thrust. So we call this quantity specific impulse. So fundamental thing, what is specific impulse? It's a measure, let's say, of the quality of the thrust, is how much costs in terms of propellant to get a given amount of thrust. It's the first thing that you should have in mind. Then we can try now to, let's say, go around and see some other definition, as we will see in a minute. But this is the fundamental thing. It's a measure of consumption. When you're using a thrust for mean, of course, consumption is always important, perhaps because of the cost of the gasoline or of kerosene. But here is even more important, because it's not only matter of cost, but it's matter of making possible or not emission. Because if we have a tank, even in our car, if we have a tank that is so big, we are not able to move this car. We are not able to. We spend all our energy to bring our propellant with ourselves rather than refueling, for instance, somewhere and be successful. So why we call it specific impulse? Impulse is defined as elementary impulse is FDT, the force by the amount of time this force is spent. And we can also consider now that, of course, the amount of propellant that we are consuming will be exactly this MPDT. So if I consider the impulse, it should be the integral of this quantity, and if F is dot MP UE, we have this, so we can also write this in this way. And in case this quantity is constant, it becomes, if our exhaust velocity doesn't change in time, we have that this is exactly. So you see from this expression that the impulse given during the time lapse we are considering by our engine is proportional to the propellant mass and to this equivalent exhaust velocity of specific impulse. And so we have that this is equal to impulse divided by propellant mass. So this is the specific impulse. The specific impulse in terms is the impulse for kilogram of propellant, for mass of propellant. So this is the reason of this name. Of course, it's also equal if we go, you can identify an instantaneous value. It would be the elementary change of impulse and the elementary change of propellant mass. You see here these two expressions, and it will be F over dot MP. Okay, so the specific impulse is also equal. This is an average specific impulse, and this is an instantaneous specific impulse. Unit of measure, meter per seconds. And this is something that is commonly used today in Europe as a unit of measure of specific impulse. You can find a velocity. Historically, this specific impulse was made in terms of weight rather than on mass. And so it was the impulse with respect to the weight of propellant consumed. So the weight should be everything multiplied by Z0 or and here we have velocity divided by an acceleration, and so the unit of measure is in this case seconds. And so we are used to consider a specific impulse in seconds. The nice thing of seconds is that unit of time has always been the same everywhere, independent if you are using feet per seconds or pound forces or so on. So between metric and imperial measures, we have always the same unit of measure, and this was also success of using this unit of measure for the specific impulse. So it has been used with this unit of measure along since many years, so we can continue to use it, and we have to be aware of this use, but consider, of course, this is just a constant multiplying our equivalent exhaust velocity. So at this point, it could be interesting to see what means this time, these seconds. And at this point, we can say, well, is the time a given amount of propellant is able to provide a thrust equal to its weight. Because if you put it here, of course, this impulse is F by T, we see that this time, if the force is equal to the weight of the propellant, we see that the ISP is exactly this time. The time this propellant is able to provide thrust, this engine is able to provide a thrust equal to the initial weight of the propellant. But when I ask you what is a specific impulse, what is the meaning of specific impulse, what will be your first answer? If your colleague asks you what is the meaning of specific impulse, you will say how many seconds this propellant is able to provide a thrust equal to its weight. Your friend, who is not working in this field, is so happy of this answer from you? I don't think so. What's important is that it's a measure of our specific consumption, of how much propellant I need to get a given amount of thrust. This is the correct answer. This is the important answer. This means, if you give this answer, means that you have understood why this quantity, and we will see all along this course, you understand why this quantity is so important. It's the, let's say, king parameter of rocket science. So there is another parameter, another figure of merit of rocket propulsion that I would like to shortly introduce. So I introduce the total impulse. Yes, just this, and a few more words. So another important parameter is related to thrust. Of course, we have to provide a given thrust. So of course, thrust is another parameter. I say, of course, it's an important parameter. It's our goal to provide the thrust. So I don't want to diminish its importance. But in principle, we will underline more continuously that we can manage thrust. We cannot manage more than a limit of specific impulse. We are considering two different quantities because one is something intensive, another one is something extensive. I can, we will see that we can not achieve any specific impulse, but for a given specific impulse, we make a bigger engine and we get more thrust. We can consider two engines and we have twice the thrust. We can consider three engines and we have 3 times the thrust, and so on. So thrust, it's our goal, it's our requirement. Specific impulse is the measure of the quality of our engine in getting this thrust. So this is a quite important remark. In terms of thrust, the different kind of engines I listed last time in our classification are characterized by different values of another important quantity, which is the thrust to weight ratio. This quantity makes different the use of different families of rockets. Is the ratio, let's say, between the thrust and, of course, this is a force, so we have a dimensionless quantity if we divide by another force, which is the weight, and in this case, let's say M0 G0. So what is this mass? It can be considered as everything except the payload. That means it's the mass of propulsion system, including the engine and the propellant in general. And of course, this depends on the specific launcher or spacecraft you are considering, because the amount of propellant is the amount you need. And so can assume different values. But there is also a limit that we can go, and this the minimum amount of propellant. So we can consider just the engine, just the rocket engine, without the propellant and so on. And so we can consider with a small amount of propellant, with a large amount of propellant, but of course there is a minimum, and the minimum mass that you have to consider here is the mass of the device itself without propellant. So we can consider for the different kind of rockets a range of values of this thrust-to-weight ratio. And there are rockets where even if you consider just the mass of the engines itself, this value is far less than 1. That means that they are not able to lift themselves. And they, for instance, they cannot be considered for a launch system. So just to, of course, you can use this kind of quantity also in aircrafts. Typically, you have their values of order 1. Important thing of rockets is that, especially of thermal rockets, is that they have value of this ratio that can be even as high as, let's say, order of 100. And this is a quite important property because it means that if we go without propellant and we have 100 just for the engine, you can consider that this engine can lift a mass which is 100 times the engine itself. And this, of course, allows us to make launchers. So let's just list some values of both specific impulse and thrust-to-weight ratio for this in seconds, and this is dimensionless. We have chemical rockets. We have a maximum specific impulse that can be reached, which is about 460, and we have values of thrust-to-weight ratio going from 0.01 up to 100. nuclear thermal rockets are also able to provide, well, they are able to provide high specific impulses. These are demonstrated values. And up to 30, something less in terms of thrust to weight ratio, because we have a nuclear reactor on board that is not so light. And then we have some electric propulsion, electrothermal. The sister jet and dark jet, which are, it can have even higher specific impulses. Recall, this means that a nuclear thermal rocket can have, can consume half the amount of propellant of a chemical rocket. So if this measure of consumption, the specific impulses, is twice, that means we can save a lot of propellant from this this ratio. These arc jet devices can even improve the specific impulse. But for these electrothermal rockets, we have values quite less than 1 in terms of thrust-weight ratio. And this is even worse if you consider ion propulsion, which is characterized by, this time, electrostatic propulsion. And we have very high specific impulses up to, let's say, it's an order of magnitude 5,000, but in principle we can go even to higher values, but 10 to the minus 6, 10 to the minus 4 thrust-weight ratio. So it will be different that you are squeezed by an acceleration coming from an ion rocket. This doesn't mean that this is useless, because if you have time, you can change your velocity slowly with a little acceleration in a long time and save a lot of propellant, because we have a very high specific impulse. So there are different ranges for the different kind of rockets. You will have here, for instance, ion, and you will have here nuclear thermal rockets, and here chemical propulsion. And then we can extend here with different regions, or arc jets or resistor jets. And here we have a family of chemical rockets which are monopropellants and cold gas. We mentioned cold gas rockets in our list. And these are log scale of both quantities. You have this distribution. If you need that specific impulse and low thrust-weight ratio, you can move towards ion propulsion. If you need the opposite, high thrust-weight ratio, you should move towards chemical or nuclear thermal propulsion. And recall, high thrust-weight ratio means also possible high acceleration, so you have to go to control this, because high acceleration can be, of course, a problem, but means also high acceleration may be also a need to make a change of velocity quick. And you have also, in terms of trajectories, for instance, if you consider an impulsive maneuver, it means that you don't have gravitational losses, and you spend, let's say, less propellant to get the same change of orbit. We will mention probably also this. Well, and at this point, we just say we have introduced a couple of other quantities in this discussion. One is the initial mass, another one is the propellant mass, and of course, if we make this difference, we have the final mass of our device. And we will use, I also mentioned, talking about the total impulse of burning time, which is the time, of course, I'm accepting this thrust. Here we start to talk about different masses, and we have to be also here, we have to be skilled about these masses. The meaning of these masses is we have to be able to define this mass as propellant mass or not. The same propellant can be considered as propellant or as payload. For instance, if you have the spacecraft, which is the payload of a launcher, it has some propellant on board. If you are making the analysis of this launcher, you will not attribute propellant which is on the spacecraft as a propellant mass, even if this is a propellant. So we have to be clear about the meaning of these masses, but this will be the topic of the next class. I stop here today, and again I apologize for the delays coming from the bad use of colleagues about this the devices we have available here.